Thank you very much. My name is Oliver Schib. I am a postdoc at the University of Bern. I'm very grateful for being able to be here and talk to you. It's really great. I think my talk should connect rather well to what Ruth has told us. Today I will introduce you to DIPSY. DIPSY is a disk instability population synthesis, and it's all new. In fact, it's just been published a couple of days ago in ANA, 2 papers. So disk instability has usually been an attempt at trying to explain planetary mass objects at wide separations. And this has become even more intriguing now that we actually have detected H-alpha emission of a number of such objects. Here you have 2 examples, AB Auriga B and WISP P2b. Super Jupiter mass objects are tens of AU with accretion, so they are probably young, they're probably still forming. But I think disk instability can be much more than just that. I think it's really a fundamental process that may be happening in many systems, and its consequences for the star and planet formation are not yet completely explored. So what is it doing? Okay. So I don't need to introduce it anymore. I think Ruth has done a wonderful job of introducing it very thoroughly. Here is a result from a hydrodynamic simulation where you can see what happens to a disk if it's massive enough to fragment. Here we see a number of fragments forming and interacting with each other. It's quite a chaotic simulation. And how do we now proceed to perform a population synthesis with something like this? Maybe just very briefly historically. So it's actually been proposed for the formation of the solar system a long time ago. This idea has clearly been overcome by the core accretion model, and GI has been disfavored. One aspect is the production of a solid core, but we now know that disk instability could also produce solid cores, or maybe cores are not that solid at all. That it can't produce low mass planets. Well, maybe it can't, but maybe it can, based on some new results. And then the next thing, people usually said that the clumps, I call them clumps when the disk fragments, then first you have a huge ball of gas. It has a few Jupiter masses and a few AUs in size, so a very extended object. And people thought that they will be disrupted. And yes, they can, but not necessarily, because these objects are a little like first cores in star formation. They contract, and if they reach a high enough temperature in their center, they can undergo dissociation of molecular hydrogen and have a dynamical collapse, which will make them a compact object. And if that does happen, then they will be really robust to disruption. Clearly, there are open questions about what population can we expect from this mechanism, and what will be the composition, and the numerical challenges are huge. We tried it anyway. So here is a little overview of how we do this. So we consider a star in the disk system with stellar evolution. The disk evolves according to a variable alpha, and we have accretion on the star. The star can irradiate the disk, and we also consider both internal and external photoevaporation. And that's a very important ingredient, we also consider the infall from the molecular cloud core. So in fact, we are actually forming the star and disk system as the simulation evolves. We start from very low star and disk masses, negligibly low, and the majority of the mass is actually added to the system during the simulation. And that's key, because we really want to study those systems when they are youngest and most massive, because that's when they are most prone to fragmentation. So in more physical terms, this is the equation that we solve. It's the well-known viscous evolution equation, but with a lot of added features. So, for example, we have this exchange of angular momentum between companions and the disk, which we developed. We developed this method in a separate paper. And we also have, we consider the conservation of mass by when the disk fragments, the mass is actually removed from the disk and put into the fragments. And the fragments, as they evolve by not only by migration but also by gas accretion, they remove more gas from the disk, and if they are disrupted, that material is actually returned back to the disk. And an important ingredient here as well is that in the irradiation model where the star can heat the disk, we also include an accretion component. So as disk material accretes onto the star, its luminosity is increased many times, and this is actually important because it will heat the disk, and the hotter your disk is, the less likely it is to fragment. So this is really a key parameter to determine whether the disk fragments in the first place. We also consider the autogravitation of the disk. By the way, I apologize for the many formulas. It will get better, but not just yet. So, which leads to a slight hastening of the disk's orbital frequency, and it compresses the disk a little in making the aspect ratio at large separations a bit smaller, both of which translate into a different Tumor Q parameter, so it also affects the fragmentation. And then, as I already told you, we have a variable alpha, which tries to take into account the different phases such a system can undergo, including global instabilities, at the very early stages, and the transport of angular momentum by spiral arms as the disk becomes gravitationally unstable. So that for the star and disk system. Now, of course, that's only the beginning. When the disk does fragment, and it does in some cases, then we introduce these clumps into the disk. And now, of course, we want to track their evolution in as detailed a fashion as possible, because we are really interested in what happens to them on a long time scale. So can these things, which are quite transient in nature, can they survive on a million-year time scale? So we have a simple model for the clump. It's essentially a ball of gas, but we consider its contraction and heating in the center. And this, as I told you, can lead to a dynamical collapse if it becomes hot enough. So that would be an individual clump, but it's also irradiated by the disk. So if it migrates in, it will feel a hotter environment, which will influence its contraction, so slow it down. At the same time, these clumps can accrete gas, and while they migrate. And now, if this was not already enough, we also need to consider that when they migrate in quickly, they could overflow their Hill sphere and they would lose mass or could be completely disrupted by tides. And of course, as we have seen in the hydrodynamic movie, usually these clumps will not be alone. So there are other clumps around, and they will also interact with each other gravitationally. So this as a little sketch of all the things that are going on. And of course, we want to take them into account, all of them at the same time. So for the internal evolution of the clumps, we rely on existing simulations of clumps in isolation, basically stellar evolution codes that solve the standard structure equations. So this is the result. You see here the radius of the clump as a function of time. These are now clumps in isolation for different masses, and at some point you reach the dynamical collapse where the radius drops by several orders of magnitude. And it's important to note that this is this has a very strong mass dependence. So more massive clumps can collapse much more easily, and thus when they accrete gas, this can also shorten the pre-collapse timescale. Okay, for the irradiation of the clumps by the disk, because we rely on tables of clumps that evolve in isolation, we now take into account the disk irradiation in a way that makes the clumps contract slower, basically by an energy balance argument, as you can see here. Okay, now maybe it's enough of all the formulas and the theory. Let's take a look at what this actually looks like in action. So this is now not any longer the result of a hydrodynamic simulation, but it's actually one system evolving from the DIPSY population. And you can see that this disk fragmented and produced already a number of clumps, and they interact with each other. You can see that there are close encounters. The disk reacts to their presence, and now you could see that there was actually a merger and another one. And now you can see that the several clumps evolving at the same time will actually produce a gap in the disk between 40 and 60 AU. Okay, so a few results. So we simulated 100,000 such systems, and we were really surprised that actually all of them, almost all of them, had a phase where they were self-gravitating, which means the tumor Q parameter dropped somewhere below 2. And we are considering objects that have a final primary mass from 0.05 to 5 solar masses, so quite a large range. And while almost all of them actually underwent at least a short phase of self-gravity, only a fraction, roughly 10% of them, actually fragmented. So that's quite the opposite. A lot of self-gravity, little fragmentation. But then again, if we do see fragmentation, then in many systems we actually see a lot of fragments. So tens, in extreme cases, even 100 fragments. And when we now look at a very long time scale, so we run these simulations for up to 100 mega years, if necessary, we can see that roughly half of the systems that ever fragmented have at least one surviving companion. So again, it's quite an extreme scenario. You have a lot of fragments that form initially, but when you look at the whole evolution at the end, only very few actually remain. So it would be interesting to see, well, what happens to all the other fragments, the ones that formed, but did not survive on a long time scale. So this is some statistics here. They collide. So due to A, the number of fragments that we have, and B, their huge size, at least early on, the collisions are actually very likely. More than 60% are actually lost in a collision where we assume that one object survives. And the ones that do not collide, well, most of them are actually ejected. So this really gives rise to a large population of free-floating objects of a more massive nature. Among the remaining ones, many of them have a thermal disruption as they migrate inwards quickly and the disk becomes hot. Some manage to actually accrete all the way into the central star, and less than 2% survive. Okay, so let's now look at mass semi-major axis diagram. The diagram is color-coded by mass, so if you just judge by mass what objects we have, then actually the majority of those 7,400 surviving companions are actually in the brown dwarf mass range. Some of them are even low mass stars, and a few, not much more than 10%, are actually in the planetary mass regime. And what's interesting now here to see is this intricate shape of that population. It's a bit like an inverted rotated L, where you have really this band of massive brown dwarfs across many separations. But the lower mass objects, especially in the planetary mass regime, actually almost all of them are at hundreds or even thousands of AU. The gray bar to the right would just indicate that, I mean, these objects are already quite loosely bound, and they could also be removed by flybys of other stars or similar effects, which we did not consider in this study. And also interesting, you see the final masses are really high, but the typical initial masses of these objects are on the order of a Jupiter mass. So they typically grow by at least one order of magnitude in mass by A, accretion of gas, and B, by collisions with other fragments. We can also now look at the eccentricity and inclination distribution, and as you would probably expect, this hugely dynamical character of these systems leads to really eccentric and also quite inclined companions. We have been talking about mass functions a lot. So here is the mass function from this population. Again, with planet brown dwarfs and stars, and I also indicated the Chabrier system IMF here in this extrapolation in the dotted line, which approximately fits. So you could interpret this now as a low mass tail of a stellar population, but I think this is subject to some discussion. So it's really just a possible interpretation. But now so this is now for different classes of primaries, and now let's look actually at the mass function of the ejected population. First of all, you realize that's actually much more ejected objects than the bound ones that you can see at the bottom. And second of all, you can see that the mass distribution is different. So it's more dominated by lower mass objects than the bound population. Okay, those are my conclusions. So it seems that disk instability can indeed produce many companions. Almost all systems have a self-gravitating phase, and when fragmentation does happen, it produces a lot of fragments and many ejected objects. One thing that we want to do in the future is really to look at more detail at the solid content of the disks, and I think with upcoming observational facilities as well as existing ones, the time is really right to look at disk instability again in more detail. Thank you very much.
Thanks. Could you go back to a slide where you outlined the process? Go back. Yeah, keep going back. Oh, right. Oh, you passed it. Go forward. Yeah. One more.
Sorry.
Keep going forward. Right there. Just hold it right there. Okay, very good. So 100,000 stars and this system, 9% self-gravitating. Very good. And 10% fragments. So correct me if I'm wrong. So if I understand correctly, what you're doing is that you let the system evolve, and then once spiral arms show the evidence of fragmentation, you remove that and by hand introduce fragments. Is that correct?
So what we do is we take the tumor Q parameter and we look, because this is spatially resolved, right? So we see where it drops below unity, which is typically at tens of AU. And if it drops below unity and an additional cooling criterion is satisfied, then we remove the mass, and the mass is the poly mass, basically.
Right, and then introduce the fragments. And,
exactly.
Right. So basically, that's my question, that why is it that you don't allow the spiral arms continue evolving and naturally produce fragments?
What do you mean by naturally produce fragments?
So when you have a spiral arms,
yes,
they gravitate, right? And they,
yes.
And you continue running the evolution of the spiral arms until the spiral arms within them, those particles comes close to each other, stay together,
Okay, yeah. Yes, I mean, that's really the assumption that the fragments form in the spiral arms. But since we are running the population synthesis in a 1D mode, I mean, the hydrodynamic forces are not correctly represented there. So you cannot, the physics for the actual fragmentation is not part of this equation. So we really need to rely on the hydrodynamic results, which tell us that when the tumor Q parameter does drop below unity and this can cool, that we then see fragmentation.
Okay.
Yeah.
Okay. Thank you. Okay. Let's thank Oliver again.